Right now, next to one of the brightest stars in your summer sky, something is firing protons across the galaxy at energies no machine on Earth has ever touched. Not mega electron volts, not giga electron volts. We're talking over 1 quadrillion electron volts. 1 PeV. More powerful than the Large Hadron Collider. The biggest, most expensive particle accelerator humans have ever built. Buried under the border of France and Switzerland. Run by thousands of scientists, decades in the making. Its absolute limit sits around 13 trillion electron volts. What we're about to describe blows past that by a factor of 10. And nobody built it. Nobody switched it on. Here's the twist before we even start. The star isn't the source. Altair is just the landmark. One of the anchor points of the summer triangle. Easy to spot on any clear night. One of the closest bright stars to our own solar system. The real object sits right beside it, in the same patch of sky, and until a few days ago, nobody could prove what it actually was. Let's back up. For more than 100 years, scientists have known space is soaked in cosmic rays, charged particles, mostly protons, screaming through the galaxy at unbelievable speeds. Some of them slam into our atmosphere right now, as you're watching this. They've been doing it since long before humans existed, and they'll keep doing it long after we're gone. The problem was never whether they exist. Physicists confirmed that over a century ago, back when a scientist carried an electroscope up in a hot air balloon and found radiation getting stronger the higher he climbed. Proof that it wasn't coming from the ground beneath his feet. It was coming from somewhere out there. The problem was finding out exactly where. What kind of object out there in the dark has the raw power to fling a proton to energies that dwarf anything we can produce in a laboratory? Astronomers even gave the boundary a nickname, the knee of the cosmic ray spectrum. The point where the numbers stop making sense unless something extraordinary is doing the accelerating. Astronomers call these hypothetical sources pevitrons. Natural accelerators powerful enough to kick particles past that PeV mark. And for decades, that's been one of the most stubborn open questions in astrophysics. Dozens of candidates have been proposed. Supernova remnants, pulsar wind nebulae, dense star-forming regions packed with young, violent stars. Every few years, someone announces a promising lead. And every time, the same problem shows up. Gamma rays alone can't tell you whether you're looking at protons or electrons doing the accelerating. Both can produce that same telltale glow. Both can fool a telescope that's only looking in one direction at one wavelength. You need more than a bright spot in the sky to make a solid claim. You need proof from more than one angle. 0 confirmed identifications until this one. In 2024, ground-based observatories in Tibet and China, instruments built at extreme altitudes specifically to catch these ultra-high energy gamma rays before the atmosphere absorbs them, picked up something strange near the constellation Aquila, close to Altair. They labeled it El Hayaso Junkum 199 Plasm Chosan Foyu. At first it looked ordinary, just another leftover from an exploded star, a supernova remnant like hundreds of others scattered across the galaxy, slowly cooling, slowly fading into the background noise of the Milky Way. Except it wasn't behaving like one. The object was throwing off gamma ray emissions above 100 trillion electron volts. That's not what a normal remnant does. That's not what most known objects in the galaxy do, period. Something in that patch of sky was accelerating particles far beyond what anyone expected from something that old, that faint, that seemingly unremarkable on paper. Yeah, so which was it? A dying leftover doing something that only looked dramatic from a distance? An illusion created by imperfect instruments, or something else entirely? A genuine, functioning cosmic ray factory, still active after all this time, still throwing particles across the galaxy at speeds that could shred through spacecraft shielding. A team led by Tsunefumi Mizuno at Hiroshima University decided to find out. And they didn't rely on a single instrument to do it. One telescope, one data set. That's how you get fooled. That's how promising leads have collapsed before. They pulled 15 years of archived data from NASA's Fermi Gamma Ray Space Telescope, scanning a massive energy range most surveys don't even bother covering. They cross-checked it against Fujian radio survey data, which maps the dense clouds of molecular gas drifting through interstellar space. Gas that's normally invisible unless you know precisely where to look and which wavelength to search. And they brought in X-ray readings from the Chandra Observatory, just to rule out anything the first two instruments might be missing entirely. 3 completely different tools, 3 independent angles on the exact same patch of sky. Here's what they found. The gamma ray signal stretched smoothly across an enormous range, from around 400 million electron volts all the way up past 100 trillion. No gaps, no sudden drop-off, just a long, continuous climb across 14 orders of magnitude. That kind of smooth spread is hard to explain if the particles doing the work are electrons. Electron-powered sources tend to lose energy fast against the radiation around them and leave a very different, choppier signature behind. Protons fit the data. Electrons didn't. Then the second piece landed. The gamma-ray glow lined up almost perfectly with the shape of the interstellar gas mapped by Fugen. Not a rough overlap. A close match, region by region, cloud by cloud. Precisely the pattern you'd expect if fast-moving protons were slamming directly into that gas and lighting it up from the inside, converting raw kinetic energy into the gamma rays we can detect from Earth. And the third piece sealed it. Chandra's X-ray data came back nearly empty. Barely any diffuse X-ray glow at all, which is precisely what you'd expect if this really is a proton accelerator, not an electron one. Electron sources tend to leave X-ray fingerprints behind, a kind of afterglow. This one didn't leave one. Mizuno put it simply, borrowing an old saying. 1 arrow breaks easily, 3 arrows bundled together don't. Gamma rays, radio trace gas, X-ray silence. 3 separate lines of evidence, 3 separate instruments, built by 3 separate teams pointing at the exact same conclusion. El Chaso J19++ for you is a proton pevotron, one of the first ever confirmed with this level of certainty, using this many independent checks stacked on top of each other. If you're already subscribed, you already know we chase this exact kind of mystery. The ones hiding in plain sight, right next to stars you could point to tonight, without even needing a telescope. If you're new here, this is what the channel is built around. Stick with us. Now here's where it gets bigger than a single point of light. This isn't some tiny pinpoint source tucked into a corner of the sky. The object spans more than 1 full degree across. For comparison, that's larger than the moon looks from Earth. Hold your fist up at arm's length and you're still not quite covering it. This isn't a needle in a haystack. It's an entire region, a zone of space continuously flinging particles outward, probably for thousands of years, long before anyone on Earth pointed an instrument at it, and probably for thousands of years still to come. The leading explanation right now, and scientists are careful to call it just that, a leading explanation, not a closed case, is that this is the aftermath of an exploded star. Its shockwave still slamming outward into a thick, dense cloud of molecular gas sitting nearby. That collision is thought to be what keeps accelerating the protons, batch after batch, wave after wave, pushing them past energies nothing built on Earth could ever reach, let alone sustain for centuries. It's not fully settled. The exact mechanism is still being tested, still being modeled, still being argued over in papers just like this one. But the identification itself, proton pevotron, confirmed by 3 instruments instead of 1, that part is no longer a guess. So think about what that actually means. Somewhere near a star, bright enough to spot with your bare eyes on a clear summer night. There's a region of space behaving like a natural particle collider, running without pause, without maintenance, without anyone watching it work. No human engineering, No control room. No funding committee arguing over budgets. Just the leftover violence of a star that died, still shoving protons out into the galaxy at energies we can barely comprehend. Energies that would tear through anything we could ever build to try to contain them. Some of those particles have already crossed the unimaginable distance between there and here. Some of them are hitting our atmosphere right now while you're listening to this very sentence. Invisible, silent, unstoppable, colliding with air molecules miles above your head. And this isn't just a curiosity. Cosmic rays at these energies are a real, documented concern for anything traveling outside our atmosphere. Astronauts on long missions absorb measurable radiation from this exact kind of particle. Spacecraft electronics have to be shielded against it. Understanding where the highest energy particles originate isn't just about closing an old scientific mystery. It's about understanding a force that's been quietly shaping the environment of space around us the entire time we've been trying to leave the planet. And for over 100 years, since the moment scientists first confirmed cosmic rays even existed, we had no solid idea where any of it was coming from. Every source was a guess. Every candidate looked promising for a while, then fell apart under closer scrutiny, one instrument at a time. Now, for this one at least, we know. Which raises the question nobody's fully answered yet. If one Pevatron was hiding in plain sight this whole time, sitting quietly next to a star half the world can see without a telescope, how many more are out there right now, aimed at us, tucked beside other familiar stars we look up at every single summer, and never once think to ask what might be standing right beside them?